The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon, everyone. It's my great pleasure to be here today. Thank you, Shahriya, for the introduction. So today I'm going to talk about rapid repair of hollow core fiber-reinforced polymer concrete steel columns. I would like to thank the students who worked on this project, Omar Abdelkarim, who is now a postdoc in Canada. Ahmed Gheni is still working with me. Sujith finished his master and now working for a professional design company. As Shahriya mentioned, I started my career in Washington State University. So this is one of the very early projects that I carried out. We did assessment for the I-5 Ravenna Bridge, one of the main bridges in Seattle area. And when we started doing the assessment, we found the bridge columns over here is a hollow core columns and with a very thin concrete wall. And then we have a one layer of reinforcement, and these are our spiral. So when we try to look at the finite element modeling for the columns, we found it's very brittle. And the main reason for this is with the provided confinement, one layer of reinforcement on the middle of the concrete wall, you cannot prevent spalling, which had to happen very early, probably under a strain of 0.0025 or so on. So these are just the moment curvature with increasing the axial load. So this is the effect of the axial load. Of course, as you increase your axial load, your strengths increase, but it comes at the price of the ductility. So you lose ductility as you're moving from low axial load to high axial load. However, in any case, your curvature ductility is quite small. And we did also some finite element models. And as I mentioned, this is where you have the stress concentrations. And you see you lost almost 50%. This is the reinforcement bar over here. And you lose approximately 50% of your cross section once on the compression side because of, again, the strain. Again, Professor Leith Presley tried to look at this situation in another bridge columns, and what he proposed over here is to move the reinforcement from the middle to the outer side of the section in hope that we have the confinement of the spiral at the outer side, so this would probably reduce the spalling. Well, it did improve the situation, but not much. We still have, this is the displacement ductility over here, and this is the lateral force, and you see you probably reach barely a displacement ductility of 3.5, which is not really enough for seismic zones. Our colleagues in Korea came up with another situations where they used a double layer of vertical reinforcement, and they tie the layers together at each bar. While this is, would expect to improve the situation because now you don't have any unconfined concrete. However, looking at the costs required for workmanship here, it's quite expensive. So we would expect this, scenario here to survive the U.S. market. So what did we come up with to have a hollow core columns? This is what we come up with. We have three materials, hybrid materials. So we start with fiber-reinforced polymer tubes at the outer side. We have concrete, and then we have a steel pipe on the middle. So we have a donut cross section. So on the middle you have a steel, outer side you have the FRP, between you have concrete. So now if we're talking about, this is sponsored, as you will see at the end, this is sponsored by Missouri DOT. So the context here is bridge columns. And if we're talking about a typical bridge column 5 feet diameter, we are talking here about concrete thickness of about 4 inches. So really a very thin concrete section compared to the diameter. So we try to use the material as it best fits. And what are the advantage of the system? You reduce your material, which is a concrete in this case, by up to 75%. The pipes act as a stay-in-place formwork. We don't have a formwork. This is one of the beauty things over here. You don't need to have a formwork because the two pipes act as stay-in-place formwork. Concrete cannot go anywhere. We have a continuous confinement from inside with the steel pipe, from outside with the FRP pipe. Well, we try to a little bit remove the steel to inside, and then we have two barriers now against the corrosion protection layers, which is the FRP outside, and then you have a 4-inch of concrete, as a cover for the steel. So what we did here, we tested a set of large-scale columns. So this was actually what I'm presenting here was the first set of testing. These are almost half a scale, or 0.4 scale to be exact. So the diameter of the columns here is 2 feet diameter, 80-inch the height of the column, and this is the column head over here. This is where we apply the cyclic lateral loads. So we tested the first column here representing the existing column in Missouri. So we try to present a column that Missouri DOT is using as a main construction for bridges over here. So we have a vertical reinforcement of about 1 to 1.2%. And then we have spirals. Well, in Missouri, we don't use spirals a lot. So this is the only thing that we do extra over here. We use a spiral on this column. So Missouri just use regular hoop. And then we tested another set of columns over here with a new column. So for the hollow core columns, what we use, we have the steel pipe that's embedded into the footing. So the steel pipe went to your footing. However, the FRP would stay at the surface over here. So the reality is you don't transfer moment on the FRP. Your moment is transferred through your tensile stresses are transferred through the steel, which is embedded onto the footing. The FRP does not transfer the load to the footing. So, and then the concrete in between over here. There is no other reinforcement except the two pipes. So we did not use any internal reinforcement on the concrete itself. And this is the FRP pipe. Here we have a bunch of string gauges inside the steel tube. Each steel tube has about 75 steel string gauges. And then when it comes to construction, we use two different scenarios for the construction. The first one is stay in place for a stay in place. So what formwork for the rely on cast in place and using the FRP and the steel as a stay in place formwork. So during you do your footing over here, we embedded the steel, you bore the footing, and then we have the FRP after this, and then bore the concrete between the two pipes. The other scenario that we did also is to have the column as precast and use a circuit connection to insert the steel pipe into the footing. So we tried both of them. So here is the columns after, well, there is a separation over here. It's not clear on the pictures, but it's not a bent. These are two different columns, two separated footing. The one to the left here is the conventional reinforced concrete. The one over here is the one with the glass fiber. So here is the test setup in Missouri. S&T, so we fix the column to the lab strong floor over here. This is the footing. And then we have two actuators over here. The actuators is going back and forth to mimic a cyclic load. This is the axial load. We have load cells and the hydraulic jacks over here to keep the load constant, the axial load constant during testing. So this is, as I mentioned, we have two phases of this project. So this is the set on the first phase, 5 columns. The first one on reinforced concrete, and then 4 different hollow core columns. We look at different parameters. The first one, as I mentioned, this is our reference. So these are the reinforcement. We have a spiral number 4 at every 3 inch, and then we have 8 number 7. For the second one, we have FRP thickness of 3/8 of an inch, which is quite thick one, and the reason here is epoxy. And then the third column, or the second with the hollow core, we have 1/8 of an inch pipe, and we use also isopolyester as a resin. So the move from epoxy 3/8 to isopolyester 1/8 is just to reduce the cost of the construction. The isopolyester pipes, our bridge division, use it already on drainage system for bridges. So the idea is to use a product that they are familiar with, that's a low cost as part of the construction system. And then one of the things we look at the steel tube thickness. So we use a 1/4 inch here, use 1/2 inch. And then on the second phase, what we did actually is focus more on the thickness of the steel pipe. So we went really very far on the steel pipe thickness to D over T, you know, on the AIACC when it comes to steel buckling, you relate the diameter of the column to the thickness. So over here it's quite, you know, 32 and 64. On the second phase, we actually went up to 250. So we went really for a very thin steel pipe. Again, the whole thing here is to try to optimize the capacity and the cost. And then we look at the concrete wall thickness, 4 inch versus 5 inch concrete wall thickness. Here is just the test. So accelerated mode, so we apply the force back and forth. This is just the beam over here, I'm sorry, but it just try to prevent the footing from going uplift, just to fix the footing to the lab strong floor. So you see the opening over here, because the FRP is not embedded into the footing. Here is the applied load. So at each displacement level, we apply 2 cycles, and then moving from one to the next one, we increase the load by 40% or the displacement 40% compared to previous step. Well, once we have done with testing, the MoDOT was really looking for, okay, what's next? What if we implement it in the field and then we hit by an earthquake and would like to repair the column? Do you have a solution for the repair? So this one was one of their questions. The other question was, what if a vehicle impacted the column? Okay, so we run the vehicle impact analysis as well. It's not presented today, but we did the vehicle impact analysis. Today I'm looking more for the repair portion of things. Okay, so if you remember, I said we have 2 different pipes, the one with the thin pipe, the one with the thick pipe. For the thin pipe, the column fell early, as you will see. So what we did is we went back and removed the shredded part of the pipe, and then we wrapped 3 layers of glass fiber. So in other words, we investigated how much confinement required to achieve a better displacement or a high displacement, and then we apply a wet layup of FRP over here of glass fiber. In a typical scenario, you need 1 week, like where the recommendation of the manufacturer, you need 1 week of curing, right, for the epoxy resin after you apply it. Well, MoDOT would like, would look, if you have, an earthquake, you would like to have an immediate opening for a bridge. So we're looking for rapid retrofitting. So to accelerate the retrofitting, we run a lot of small-scale testing and analysis on the epoxy to accelerate the curing of the epoxy. So what we end up is we created over here a heat chamber using this simple sonotube. So we use a heat chamber over here, and then we use heat gun to apply elevated temperature on the resin. So we apply a temperature of 50 Celsius, about 120. So we apply 50 Celsius on the resin using the heat guns for 4 hours. So instead of 1 week of curing, we cut this only to 4 hours. Wrapping itself took about 1 hour. So we have 1 hour for wrapping, 4 hours for curing, so a total of 5 hours. And then once we have done with the 4 hours of curing, we start to inject a very fine grout just to fill any cracks on the column. The injection itself took about 1 hour. We didn't have too much spalling over here because of the pipes that we used, so we didn't have too much spalling over here. So the total thing took only 6 hours. Wrapping 1 hour, 4 hours of curing, injecting epoxy grout for another 1 hour. So it's 6 hours, and we're ready to test the columns. However, because of the it was come at the weekend, so we're not able to test the column. So anyhow, we tested the column after 22 hours from finishing. So in total, we tested the column after 28 hours from starting the repair. So here is the column And again, this is the opening that I mentioned several times because you did not embed the glass fiber. And this is the column and the failure here. So these are the different failure modes. This is the reinforced concrete, the reference specimen. You can see here some buckling on the vertical rebars, and also we have some bar fracture over here. These are the two FRP, the hollow core columns. The first one, this is the one with the thick glass fiber. So this is a 3/8, and this is the thin glass fiber. So both of them fail more or less at the plus or minus 53 angle. This is the angle of the fiber. So when we did these glass fiber are filament winded at plus or minus 53. That's mean you have, and this is your fiber. You can see over here. This is the angle of the fiber 53, and this is where you obtain your failure at this angle. This one here is interesting. We did a lot of finite element analysis to determine how much embedment depth is required for the steel tube inside the column. So in order to verify is our finite element is correct or not, one of the columns intentionally we did it with a shorter embedment depth. So we did all the columns, as you will see later. So these two columns we didn't have any problem with the embedment, but in this particular one we had a shorter lap splice to calibrate kind of our finite element models. As you would expect, if you have short embedment depth, we get the pull-out failure, and we had damaged footing, which you wouldn't like. So this is just a pull-out failure. This one over here, we achieve a different mode of failure. So again, the objective here is we try to see with different parameters, we try to explore the different failure modes. So over here, we get a significant buckling on the steel pipe. As you will see over here, the buckling over here. This is comparison. This is the thin glass fiber. This is the first test, and then after repair, this is the column after repair. So we really, after repair, we did not rupture the FRP because again, this FRP equivalent to the 3/8 of an inch pipe. So we use really a more thicker FRP, so we did not rupture it, and it failed very much similar to the column with the thick glass fiber. So we inserted some telescopic camera inside the columns, and just the goal here is to see how is the column from inside, how are the steel pipes working. So this is the surface of the pipe, and this is the bottom. So we are looking from top. So this is the surface. You can see here the corrugation. This is just on the compression, buckling of the steel pipe. You see over here all this folding. You are buckle the steel. However, once we start remove the loading, you would find release of all these buckling on the pipe. This is another one. This is another column where we have more severe buckling. So the second one actually from the repaired one. And here we have a comparison between the original column. So this is the hysteretic response of the column. So on the vertical axis here, we have the moment calculated by the measured lateral force times the lever arm, and on the horizontal one, we have the lateral drift. The blue one over here, this is the original column, and the red one is the repaired one, the 6-hour repair. So if you look over here, strength-wise, on one side, we came short a little bit of the strength. On the other side, we reached the same strength. However, it's amazing that we are able to exceed the energy dissipation and displacement capacity of the original column. Again, this is just because you have extra confinement. This is just a general view of the first phase of this project. This is the reinforced concrete column. And again, nothing here. This is a well-designed, so we didn't expect any surprise over here. You get a very fat loop with a very high energy dissipation. This one over here, the hollow core columns, and if you compare this to this, they behave very much the same shape, right? Looks like, very much this one and this one looks like the same. And the reason for this, you rely on the same mechanism, right? You, on the one to the left over here, you yield the steel and so on. On the second one, we also still yield the steel pipes and so on. So very much you get, the same performance. Over here, this is when we use the very thin FRP. Strength-wise, this one and this one perform the same from a strength perspective because it is the same steel pipe. However, because we had a thinner pipe for the FRP, you get less confinement, you achieve less displacement, and this is the difference between this one and this one over here. On this column over here, this is where we had a shorter lap splice, or sorry, is a shorter embedment length, and this is where you see some of the slippage over here at the over here. This one, we increase the thickness of the concrete. It behaves very much similar to the other well-designed column. Well, here is a lateral a comparisons between the lateral force, lateral displacement versus moment. This is a backbone curve for the different specimen. The original one, this is the reinforced concrete one. As I mentioned, it behaves very ductile. It's well designed. This one and this one here is the one with the thick FRP. This one here is the one similar to this one, but with a thinner FRP. And this is where we have the pull out. So the pull out, we have a higher load because the thickness of the steel is higher, but it's not as ductile as the original one. Over here, we have the comparisons between the red one over here is the repaired one. This is the original column, the reinforced concrete reference, and this is the thinner FRP. So this red is a repair of this magenta one. So as you see over here, we are able to more or less reach very close here in about 10% difference between the original and the repair one. However, in terms of displacement, this is performing much higher. In terms of initial stiffness, we cannot restore the 100% initial stiffness. Again, our system, we did not touch the steel, which already has some residual stresses on the steel, and this is why. Plus, also you have probably some micro cracks in concrete. And then we end up with also preparing a simple calculations and calculations or Excel sheet calculations for the DOT. So in other words, on one side you have dilation of the concrete, and which push versus the steel, and then pushing the FRP. And here also some interesting measurements. What we found here, the system is really a very dynamic system. That means you have interaction between concrete, steel, and fiber. Concrete in compression start to dilate. Okay. Now the question is which direction the concrete would dilate. Would it dilate versus the steel or versus the FRP? It all depends on the relative stiffness. So what we found, so these are very much the same. The only difference is the steel. So whenever you have a thicker steel, concrete can find it's hard to propagate toward the steel, so it pushes versus the FRP and ruptures the FRP early. If the FRP is the one that's really relatively thick compared to the steel or more stiffer than the steel, concrete push versus the steel and the steel buckling happen quite early. Well, I'm just skip to the conclusions because of the time. This is also some equation that we developed for how much required development length. And then with this, I reached the conclusions. We're able to provide the industry and researcher with a hollow core columns that able to sustain and display high energy dissipation and also high drift ratio. And also I would like to thank my sponsor, Missouri DOT, Mid-America Transportation Center, National University Transportation Center. Thank you so much for your attention.